All right. Hey, everybody, and welcome. Let me get the background noise a little bit. How are you? How is Global Hack Week going? Let me see if there was a stream. I think there was a stream before us here. Intro to C++. Did anybody catch that? With Chargle? C++, I mean, that's a great thing to know about. Let's take a look. Oh, hey, Courtney. Good to see you again. Yeah, I wonder, did you catch any of the streams today, except for the last one? Just curious if there were any good, particularly good ones today. I know Quinn did one on interpretable LLMs. That sounds really interesting. Bummer that I couldn't go. Had to work. Yeah, so today we're going to be talking a little bit about reinforcement learning through what we call the Markov decision process algorithm. So this is a reinforcement learning, or RL. Okay, so has anybody here maybe heard of RL? You might have heard of it recently because it's used by a lot of the new LLMs. The ones made by ChatGPT, for example, use reinforcement learning from human feedback, or RLHF. And looking forward to the Pokédex. That's really interesting. Who was that? Do you know who made that one? Oh, looks like that was with Alberto. He's really, really good a streamer. So that probably was really fun. I'll have to check out that recording too. And by the way, if you miss any of the events and you want to see the recording, feel free to take a look. Okay, well, why don't we get started? But before we do, I want to give you all the check-in link. The check-in link is really important to fill out because it really helps us with our data collection. We want to know, what times are people available, what times are people interested in going to a stream, and really what content you want to see, right? Because if a lot of people check in, we know that it's really popular. So go ahead and fill out that form for us, and you'll see. You might also get some swag. Oh, okay. Sorry about that. Yeah, I did put the wrong link. Sorry about that. Hang on, let me put that right. This one should be better. 12481 is the event. All right, so this is a little bit of a puzzle. I love a good puzzle, and I hope you do too. The markup decision process is where you ask the algorithm to design a policy which will best fit a scenario. So a scenario, in case you don't know about this, it's where you have states, transitions, actions, and outcomes. So I'll try to give you an example of what this means. You might have a state where, for example, the forest is in a young stage. So new forest, right? The forest could also be in a very mature stage, and that would be more of a higher state, right? The transitions, on the other hand, is where you are transitioning from one thing to another. So, for example, you could transition from, let's say you have some milk, you could transition that into milkshake, right? And then actions would be things that the system can do. So you might have the ability to drink or stir your milkshake, and the outcomes might be that you might be rewarded. So in a business, for example, one of the outcomes is to make revenue, right? So we could design all kinds of policies that would optimize for a certain outcome, whether it's we want more money from the business, we want to get a good positive rating from the user in the case of ChatGPT, things of that nature. So I'm going to give us a scenario to practice, and this is going to be a travel scenario. So the travel scenario is a trip from San Francisco to Los Angeles. Does anybody here know these cities, or have you ever been here, or maybe you've heard of them? Personally, I've made this trip before. I've only ever done it by car, but I know people who've done it by plane and train. It's a really common trip because these are some of the biggest cities on the west side of the US. So basically, if I were to ask you what's the fastest way to get from San Francisco to Los Angeles based on this map, you can see that the plane takes about 1.5 hours, the car takes 6 hours, and the train takes 11. So if you were to think about, okay, what's the fastest way to go, you probably think that's the plane, right? But we actually have two other ways to go. So we would always choose the plane if we wanted to get there fastest. Now I'm going to complicate this a little bit, and I want you all to think about this. So first complication I'm going to add is that, let's say with the car ride, we currently have a 6-hour car ride, but let's add a little more realism to this. Let's make it a little more realistic. So let's say that there's a 10% chance that there's some severe traffic along the way, right? If that's the case, how long would this car ride take? Well, on average, it's now going to take 6.6 hours, right? Because we can multiply 10% by 1 hour. Okay, That shouldn't come at too much of a surprise to all of you. But let's add even more complications to this, okay? We're gonna talk about how complicated it can be to fly an airplane. So here's one case. Let's say we have a 10% chance of a security delay, which could cause a 2-hour delay. A 25% chance of a plane delay, which could cause a 3-hour delay, and a 5% chance of a deplane delay, which is when you're getting off the plane. Maybe there's a delay, they forgot the ramp or something, they don't have one for you all, so you gotta wait an extra hour. Oh no. But now we're really getting into some complicated, decision making here. So what would you do in this case? Let's say these are your options. What's the fastest way, even with all of these delays? Is it the train? Is it the plane? Well, think about the plane. So we take 1.5 plus 10% chance of 2-hour delay. So now we're at 1.7 hours. And then let's say we took out of 0.8 or 0.9, 0.8, let's say, from the plane delay and the deplane delay. So we're looking at a much faster way to get there from the plane still, compared to the other methods. But now I'm going to give you a new task, okay? So this task is, what if I want to guarantee that I arrive in 7 hours or less? Okay? If you want to guarantee that you arrive in 7 hours or less, well, in this case, I don't think you can take the plane, because think about it. If everything goes wrong, you're going to have a plane ride of 1.5, a delay of 2 hours, a plane delay of 3 hours, and a deplane delay of 1 hour. So how much time is that in total, right? Well, that's about 7.5 hours. That's going to be too long. So what's the best way if I want to guarantee that I arrive in 7 hours or less? Can anyone say this? It's actually quite a complicated question. Okay, so great. Thanks for giving me an answer there, Pi Engineer. Let's see if it could be the car. So in the car, you will have that great, guarantee, right, that you're going to get there 7 hours or less. But the problem is, so Courtney, you can guarantee it, right? If you take the car, even if you hit traffic, you're going to get there in 7 hours. But it's still going to take you, on average, 6.6 hours, which is so long, right? So I'll give you a brain teaser here, okay? Here's how you wanted to do it. You could actually do this. So let's say you start by going to the airport. You buy your airplane ticket, right? And then after 1 hour of being at the airport, if you have decided, okay, listen, I'm really gonna miss my arrival time, well, go ahead and go to the car. Because if you arrive at the airport and there's a security delay, you know that it's possible you will miss your plane. But if you arrive and you see that security delay, then you can get the car. So in this case, most of the time you'll be able to take the plane, no problem. But if you do hit that delay, you know you've got to take the car in 7 hours. And it's kind of a common sense type thing, right? Hey, I want to go as fast as I can, but I need to get there in less than 10 hours. And I guess, to be fair to you, Pi Engineer, I didn't tell anybody that I want to get there as fast as possible. But So you were right to take the car, but wouldn't it be better to get there faster and guarantee that you'll get there on time? So that's the principle behind this reinforcement learning concept, which is to basically try and find the optimal solution, right? Even if it's kind of unintuitive and maybe your algorithm could be difficult to figure out, right? So let's put this into states, okay? Just gonna map the scenario by looking at all these different components. So the first component I'll look at is states. We can say that the person's location in this process, the person's where they are or which stage they're at, is represented by the states. So for example, being in San Francisco, that's S0 here. Whereas being in the car and hitting some severe traffic is S2. So these are all different places you can be. You could be in the train at S6. Now, once you get in the train, it's pretty hard to get out of the train. So, maybe you're in S6 and you can't get back to S0. But you're definitely going to go to S7, right? Once you're in S6. So that's what we would call the transitions. I'm thinking we can map that through the state transition matrix. That's the probability that state 1 will transition into state 2, or state 3 will transition into state 4. And so looking at our example, our diagram, state 1 to state 2 is actually when a car hits traffic. And we've already said that's a 10% chance. So state P12 is going to be 0.1. That's the value of that matrix value. All right. And so this is one of the key inputs into the Markov decision process algorithm, the MVP algorithm. Another key input is the rewards matrix. And this is calculating the reward for each action. So can anyone tell me, what is the rewards system for this case? What does a reward look like here? There's actually a couple ways you could think about it, so feel free to give your thoughts, because there are a few different ways you could set up a reward here. I'll give you one way, and then maybe if you have an idea, you can take another way. So here's one way to make the reward matrix. You could say that the rewards are the time taken, right? So if you took the train from San Francisco, it's 11 hours, and you could say that that is a reward of 11. And in that case, of course, you'd want to minimize the reward, right? You'd want the lowest possible time for travel while also staying below that 7-hour mark. What if you were to define a reward that maximizes? Is there any way to define a reward that you can maximize here? I'll give you a hint. So it's actually related to how much time you would save, right? So you could say, okay, I want to get there in 7 hours, but every hour that I save under 7 hours, so 7 minus the hours it took me, that could be my reward, right? Oh, I saved an hour, I saved 2 hours. And so we could try and maximize that return while also keeping the reward matrix positive, right? So that's one way we could define the matrix as well. So we're going to give an example which has some social good benefits to it. So basically, this is forest management. Has anybody ever heard of forest management? There's a lot of this, really. Whenever you get a paper bag from the store, or you make a paper notebook, it's made from of course from trees, and those trees are coming from one of these commercially owned forests. And so typically loggers will either own land or they'll rent land from the government. And they manage the trees on that property. So they have two main concerns, right? One of the concerns is, I'll type it out here. Concern number one, keep your forest healthy and sustainable. Because if you keep your forest healthy and sustainable, it means that you're going to have enough wood for the next year, right? You never want to make sure that your trees are, all gone, because then you won't have any way to make money in the next year. The concern number two is to maximize their profits. So they want to get as much profit as possible, right? And of course, these two things are not always going to be symbiotic. They're not always going to work in the same direction. So we're going to use reinforcement lending to kind of try and solve that. Okay, so let's try and make a state diagram for this forest, okay? And I'm gonna start with a few states that we can define. So the first one I'll define is a new forest. We'll put that at S0. That's gonna be when we have a really young tree, right? Think of a sapling or something, you can actually buy these at the store, at Home Depot or at Lowe's or whatever your local hardware or garden store is. You can buy them for just maybe $100 or less, and depending on the species, of course. And then the hope is, right, you take care of it, you water it, you give it lots of sun and nutrients, it will turn into a middle-aged forest. So maybe it gets a little bigger, and let's just call that state S1. Okay, so that's our middle-aged forest. And then the final state, which we'll talk about here, is the mature forest. Here's where we get our good harvest, right? So if we take down this mature tree, we get a lot of wood to use for paper and things like that. But of course, those are our oldest trees, so it doesn't get there overnight. There's no way to plant a mature tree in an economical way and harvest that, right? So here's our states, and then let's get some transitions. So I'm going to define the first transition, which is going to be that the new forest grows into the middle-aged forest, and let's say that every year there's a 90% chance that the new forest grows into middle age. Okay. Why do you say 90%? Does anyone know what could happen to the trees here if they don't grow? Any other choice that could happen? I'll let you think about that. I'm also gonna, but maybe one. I'm also gonna give you a suggestion here that maybe they could get burned down, right? There could be a 10% chance that a fire comes and destroys them. So that's a real possibility. And then let's also define the same here for mature forests. So let's say that there's another 90% chance that they grow, but the fire risk for mature forest is much greater, right? Because actually it will destroy the tree and we have to start all the way from the beginning, right? So not so good to have to do that. Okay, and so now I'm gonna talk a little bit about some rewards matrix. And so these are some actions you can take. The first action, let's talk about, is gonna be cut. So action number one is gonna be to cut the tree. Well, what happens when we cut the tree? If we cut a baby tree, we'll probably not get much money at all, right? So probably we won't want to cut the baby tree. We'll let that one go. On the other hand, if we cut the middle-aged forest tree, now we're maybe gonna, we're gonna make a little bit of money, right? Because there's some wood there. There's potential products we could make with that middle-aged forest tree. But the biggest payoff, and this is where we get the most money, is in the mature forest. We have a lot of wood from that big mature tree. Okay? So now let's look at the action to keep. All right, and the keep matrix is going to look like this. First, new forest, baby saplings. Of course, we're not going to get any money if we just keep the tree around. Same with the middle-aged forest, but interestingly, let me tell you about a. Let me say this in the chat too. We're talking about action number 2, which is keep. Interestingly, in this mature forest, let's just say that the government will give us some money if we keep that tree around. There's plenty of government programs that do this. There's things called forest protection and conservation laws. There's also programs for carbon buyback. So people want to offset their carbon emissions, and they'll pay to keep some trees alive in the forest. And let's say if you somehow manage to bring your tree all the way up to maturity, you'll get $4 for that. Well, in this case, it might be a big payoff, even bigger than cutting it down, but we had to get the tree there. Not all the trees will get there, and there's of course always a risk that it'll burn down and become a sapling again. Or to replant, right? So I'm gonna challenge you all. Let's think through this. What is the best strategy if we're the forest managers? What's the best strategy for us? We're going to use coding to actually reinforcement learning to actually answer this question. Right, so first, let's go to this docs page, and I'm going to actually copy this link into the chat so you all can see it. And this is a link to a Python toolbox. So let me show you what this looks like. So it's called the Markov Decision Process for MDP Toolbox. It provides a bunch of classes and functions for resolving discrete time MDPs. So here's a few available modules. The first one is an example. So examples of transition and reward matrices. We're actually going to look at one of these today for our forest management. And then you also have in MDP a lot of Markov process algorithms, MDP algorithms, so we can use that to kind of construct our algorithm and optimize that. And then util is for validating and working with that. So here's just a few examples of how to report. I'm going to show you first the MDP module. So these are different ways to solve the MDP model. So we have the MDP class, the finite horizon, many ways to do this. And Q-learning in particular, this is a special reinforcement learning algorithm. It's a nonlinear algorithm, whereas finite horizon would be linear. So there's many different ways to do this. And you might want to try a few different methods if your method is not working or you want to see how sensitive your end result is to the method you use. But we won't go too far into detail about all of these because we want to talk about some of these other things. So util, this is just a great way to check and make sure that everything is working in your code. So you can check if an MDP is properly defined, that it's square matrix, so on. And then the example module. So here there's a few different examples, and I'm going to give forest as the main example for this workshop. So forest is a simple forest management example, and let's have a look at this documentation. Okay, so the way we call the MDP example is by calling the forest method here, and there's many different parameters to this method. The first one is s, and we're going to use s equals 3 to indicate, it basically indicates that we have 3 different tree states, right? And then we'll use r1 equals 4, that's the reward received for waiting until the tree matures and we get a nice mature tree out of it. R2 is going to be our reward if we cut that mature tree down. And so then one will be the, $1 will be half of that, and that'll be the what we get for cutting down a middle-aged tree. And then P, this P variable is the probability that a tree is burned down. So it's 0.1 by default, which is that 10% chance of a fire coming through. Honestly, that's probably a little high. Even in the most fire-prone areas, you probably don't have most of the trees there are more than 10 years old. So it's probably not going to happen if we lose a tree every 10 years, the same tree, but we can build that. Maybe we'll try a few variations on this. We could try some sensitivity tests on this to figure that out. But that's the P parameter. And then is sparse is equal to false by default. So you can see over here, this is just whether the probability transition matrices will be returned in sparse format or in dense format. So we're just going to give them in a dense format, and you'll see what that means when we go through here. You can even see it over here too. So if sparse equals false means that we will have a shape of A, comma, S, comma, S. So what this means is action is the first dimension, then state 1, our initial state, and state 2, the state we're transitioning to. Okay, so here we are with our code, and let's try and run this and see what happens. So I'm gonna direct you now, because we've kind of gone through a lot here, to the GitHub page, where we're actually going to do some live examples. All right, so here's the folder that we'll use on GitHub. Feel free to look into that link. It's really similar to the link from our previous workshop earlier this morning. If you were joining for that workshop, you'll know about that. But for anybody who wasn't joining, let's try and get this on our local computer. So I'm going to actually share my screen. I'm going to show you my GitHub desktop. Which, we actually did clone this already. But if you have GitHub Desktop, let me show you where you can download GitHub Desktop, which is a great tool for you to have. If you have GitHub Desktop, you can do this too. And so what we'll do is start by clicking Open Visual Studio Code. So, well, you won't have this yet, so you'll need to click Add Clone Repository. Use that link I gave you to get that from github.com, and choose your own local path in your directories to place this code, and then you'll get to this page. But you'll want to click Open in Visual Studio Code. If you don't have Visual Studio Code, here's a link to that as well. But it's really good to have that. And we'll just click Open in Visual Studio Code and see what we get. My computer's loading it now. Let's see what we have. It looks like we have some of the stuff still open from our last workshop. Here it is. Quite a bit of stuff. Now, I'm not going to re-go through this, but it was just kind of fun. It's kind of fun to see what we were doing earlier this morning. We were looking at k-means clustering and making some bullseyes, making some blobs, and classifying those. Kind of interesting. But now we're going to move to lesson 3, which is this folder lesson 3. I know they're out of order. I'm sorry about that. Let me try to actually duplicate this. I want to actually try and give it a shot to make this blank so that you all don't have to necessarily use a filled up notebook. We can actually go through it ourselves together in this workshop without using the final answer. So just hold off on copying this code for a minute while I make a blank copy here. It takes a minute to do this. Oh, I even had some kind of random stuff in there. Sorry about that. Let me delete that stuff from the bottom, because there is some like random code in there that shouldn't be there. All right, so I'm going to push these changes to GitHub. And now you can download the data. So let's go back here and check it out. So I made a blank page so that we can all follow along together with that version. And put this on the other side too. Okay, so the first thing to do is to make sure you have this going. Is there anybody in the chat who needs an extra minute or two to get this set up? All right, well, if you do, just let us know. You can also just follow along and watch the recording later to catch up. But today we're gonna start by installing this MVP toolbox. That will do pip install MVP toolbox. When we run that code, it lets us download everything we need. Really cool, huh? And so the next step is going to be to import all of these packages. So the first one we're going to import is the MVP toolbox.example module. And so this is where we'll get our random forest state transition matrices and things like that, so we don't have to write them ourselves. The next thing we'll import is our MVP module. And this is where we'll get all of our solvers and our models from, so we don't have to write our own algorithm for solving the reinforcement learning. And then finally, this is our NumPy module here at the bottom. So we have import NumPy MVP. Okay. So when we run these, they finish and we're good to go. So now let's try this out. So remember, this is our notes for the forest management example. Trees can either be young, middle-aged, or old. Each year, each trees get one stage older, so S+1 is whatever state they were. Now, of course, once you get to mature tree, you can't go any further, so this rule doesn't apply to the mature tree, but keep it in mind. And then each year, there's a 10% chance that the whole forest burns down. When the forest burns down, you're unfortunately out of luck for that year's harvest. You don't get any protection money, you also don't get any harvest money. So it's kind of a real bummer when that happens. And if the like it says, if the forest burns down, you get nothing. If you cut down the trees, you get 0 points for a young one, 1 point for a middle-aged one, and 2 points for an old one. And if that forest reaches its oldest state and you don't cut it, you keep it instead, you'll get 4 points or $4. That's one way to think about it. So given these facts, what's the best strategy to do? So let's take a look at this. So we're going to start by just making a list of all of our inputs. Okay. So, oops, darn ChatGPT did this. Okay. So S is the number of states. Remember from our documentation. We're going to say R1 is the reward from the first action, R2 is the reward from the second action, and so we'll say first of all, first action is wait, or keep, I should say. keep or wait, whatever you want to say. And then the second action is cut. And now finally, P is going to be probability of a wildfire. Okay. Now for the outputs, of course, we'll define those two just so that we know what they are. So we have P, which is the probability transition matrix, telling us how probable it is to transition from one state to another. And remember, that has a shape of ASS, right? So it's the actions times the scenarios times the state times the next state. And then the reward matrix will have a shape of S comma A. So think of it like this. You're in a current state. If you were to be in that current state and you were to take this action, what would be your reward, right? So that's how the rewards matrix works. Let's explore these a little bit. So we're gonna first define a new PP example. Use all of these. Put a tab here to fill it in, but remember I'm only using 3 right now. So S equals 3 here. So let's run this code. It'll generate those matrices for us. Uh-oh, rewards must be null negative. Oh, yeah, duh. You need to actually give a reward for these. So just the one thing is don't let ChatGPT auto complete everything for you because you'll make a mistake. So to wait, we'll get 4, and then for cutting the forest down, we will get 2. And let's run that again. And if we explore this probability transition matrix by just typing out P, notice something interesting. All right, so let's try to work with some of these things. It's a kind of a complicated array, right? You have multiple dimensions, 3 different dimensions, and each dimension has several entries. So first I'm going to just print out P0. And P0 is the transition matrix for action 0, which is keeping or waiting. And so we have that here. So let's give an example here. I want you to actually try to solve this. It's from our notebook here, our solution notebook. What is the probability that a forest in its youngest state will advance to the next oldest state? So that means the middle-aged state. That was middle-aged. If we wait. You may know how to solve that one. That's kind of a tricky one. It will follow from this P variable though, so we should be able to use P to get that. Just think about it logically too, from the slides, the diagrams. So yeah, so it should be exactly 0.9. So when you type print P0, so the first 0 is meaning when you wait, right? And then it starts in the youngest state, so that's another 0, and it advances to the middle-aged state, so that's a 1. We should get 0.9 here. And in fact, if we run this, we do get 0.9, which is great. All right, so here's another one. What is the probability that a forest in its oldest state will burn down if we wait? So this, again, we're going to start with P0. And then, again, we're starting in the mature state now, right? We're starting with a mature tree, and we're wanting to know how likely is it for that tree to go down to a young sapling. We expect 0.1. Get that. So our probability transition matrix seems to be working how we want it to. It seems to be set up just how we like it. Now it's time to do the rewards matrix. Okay, so for the rewards matrix, with R, so we run that code, we get a shape of S comma A. So S being that state and A being that action that you might want to take or not take. So let's answer this first question here. What reward do we get if we choose to wait and the forest is in its oldest state. So I actually like to do it this way. We're going to sum up the multiplication of R transpose and the state vector. So think about it this way. On the left-hand side, let's actually define this as a function. So I'm going to define it as a function, root reward. So on the first part here, we're going to say the state, right? So the state here, the action. So the action here is going to be the weight. And then the states is going to be this vector here. And we're going to return the sum of the multiplication of this. So this is what we call a dot product, actually. So we're taking the dot product of these two, the reward matrix and the states. So if we were to calculate this, we could compute the reward using the following. So we see that our action is the weight, and the forest is in its oldest state. So one tree that's really mature, and we get $4. Now you could change this state vector. You could say, okay, let's say we have 10 new trees, and then there are 5 middle-aged trees, and then we have 3 mature trees. Well, that's great. We can calculate the reward for staying with 12. And if we want to now do the reward to cut the trees down, 11. So of course we would let them wait in this case. But it's not always so obvious. So I'm not going to go through too many more of these exercises. I hope that you can kind of do some of them on your own if you are interested in further exploring these rewards matrices or probability transition matrices. I'm going to move on to what we call finding the optimal policy. Okay, and so first we're going to use a model. We need to use a MVP model. And I'm going to let's just use policy iteration for now. So each of these models is a different algorithm that we won't necessarily go deep into today. But for the sake of argument, let's just say that policy iteration is what we want to try today. And we can try it by actually running this code. So we inputted, if you can see, we inputted a probability transition matrix and a rewards matrix from our previous code. And then we gave it a value, a 0.9 value. Now, what does this value mean? Let's actually put it up to 0.99. This is a suggestion. Autocomplete, but let's put 0.9 because I have a little comment that I added here. So basically, the 99% value, this 0.99, is what we call our discount. And so, yeah. So a 99% discount says that it's very likely that the scenario will continue into the future. So this is a long-term strategy. And let's just assume that we start with this long-term strategy. So what does it mean to follow a long-term strategy? It's kind of not obvious. So long-term strategy means that all of these parameters that I showed you, this scenario that we described, you could safely assume that will continue forever and forever. In other words, it's like you would accept more risk, right? Because you know that the future will be just like the present day. And so you can accept a higher degree of risk in strategy, and it will most likely pay off. So let's now run this, and then I'm going to do the following. So we'll do model.run. So this is going to run the Markov decision process policy iterations solver, and it should solve our scenario. So let's run this. And then we can type model.policy, which will tell us the answer. So this is really interesting. So policy tells us what action we should choose depending on what state that we're in. Right? So here's the three choices here. They're all zero, if you notice that. Saying that if you have a young tree, wait till the next phase. If you have a middle-aged tree, you should also wait. And then if you have a really mature tree, you should wait again. And why is that? Well, because if your trees are always going forward and maturing, this payoff of $4 is going to be way more attractive than the payoff of $2. Right? So we have that. That's our policy. And then let's actually try to increase our or decrease our discount. So we're going to apply a discount to our model. So if we think about this the other way, 1% discount says that it is very unlikely that the scenario will continue into the future. So this is a short-term strategy. And so I'm going to make it 0.01 here, a discount. And we'll run the model again. See what we get here. What do you think the policy is going to be here? Probably won't be to wait again, right? We probably will be able to, we'll probably want our money faster. Okay, so here it is. So here's our new policy for a 0.01 discount. So this is short-term thinking. And in the short term, if you have a middle-aged tree, it's better to cut down that first tree and get those that $1 reward. Wow, $1, how great is that? No, seriously, get that $1 reward. And then if you do make it to a mature tree, sometimes you have a bunch of mature trees, yeah, stay on those, right? Keep those going, because if every year you keep them, you get $4 instead of $2 from cutting them. But eventually this forest will just become a bunch of middle-aged trees, because all of those mature trees will eventually burn down, and the manager will never let them become mature trees again, because the risk is too high, right? The trees could burn in a fire and you could lose everything. Now, what's a good reason to apply this discount where you're saying that the future is really unlikely? Well, here's an example. So let's say you have a wildfire that is getting worse and worse from climate change. In that case, you're not so sure maybe that the forest is going to survive for the next year, even though in the past it's always survived. You don't know what's going to happen now. And the same thing could be said of stocks and bonds, right? I mean, you have a pretty good track record of the stock market and what it can return each year. But if something were to change in the world where maybe some crazy new technology comes about, or society changes in a really big way, then you probably would have to question whether the stock market will behave in the same way that it always has. So those are just a couple of examples of some ways that you might apply a discount. And now I kind of want to explore the solution space with you all a little bit. I'm gonna upload these to the GitHub so that with our blank page here you can see everything and try to follow along. So that's uploaded now if you want to take a look. Just went ahead and uploaded it. But let's explore the solution space here. So let's see what we have. And feel free to follow along with this here. I had a great way of defining our examples. So we could add more trees here. We could change the rewards. We could change probability. So I'm just gonna say, I'm gonna make a new function called calculate policy, and I'm gonna put the raw inputs in here. So the default will be 3 trees, $4, $2, 0.1 wildfire, and discount of 9. So we're not going to do any uncertainty right now. Any uncertainty. So first step will be to build the PNR matrices. Second step will be to create the model. Third step will be to run the model, then return the policy, right? So let's try testing this function, actually. There was a great way to do that with ChatGPT. Yeah, there we go. So we tested the policy. It works just like our original, which is great to see. Now, what happens, I'm curious, to our cases when we increase the probability of wildfire here? So let's try to what happens if we gradually increase the probability of wildfire. Let's see what we get here. There's really interesting code generated. This is exactly what I was looking for. So, oh, even a plot policy. That's interesting. Yeah. Okay. Let's see if this works. Let's see what it generated. So it definitely did what we asked it to do for this calculate policy function. And then calculate policies is going to take multiple p-values. So we can actually range our p-values. I don't really care very much for this to be actually its own function. I think I'm just going to do it this way. So we'll do p-values, policies. I think this is a little simpler to understand than what ChatGPT generated. So here we vary the probability of a wildfire from 0 to 1, and then we'll plot the increase. So let's have a look at this. So state 0 and 2 are always going to be a weight, right? But around 80% chance of wildfire, so the chance of wildfire has to be pretty high. But then if the wildfire chance is high enough, apparently we get to this point where it's no longer feasible for us to keep the fire alive. Let's try to zoom into this, actually. I'm really curious if we zoom in a little bit. Let's try and zoom in on this transition that happened between 0.7 and 0.8. Oh, oops. We need to define these. They're already all default defined, so we'll just vary that. Okay. So it looks like the transition happens around 78 or 9%. Very interesting. Oh, I don't want that tick there. Yeah, so it looks like the transition happens literally at 80%. As soon as you hit 80%, it's like that's when we get into a really bad zone. If you think of a question to test, by the way, feel free to post it in the chat. We can test that together. I want to actually see what happens if we add more trees here. So what if we add, like, let's say 5 trees instead of just 3? Yeah, let's see how this is, why this didn't work. You can use the fix command in Copilot to fix this. Maybe. We'll see if that works. Okay. Let's try that. Okay, here we go. So, and actually, let's go back to our 0 to 1.1. Okay, so here they are. So, as the wildfire probability increases, it looks like it gets harder and harder to justify keeping mature trees around. So, you know, we have first we get rid of the middle-aged tree, then we get rid of older trees. Finally, we're almost getting rid of the completely matured trees, but never actually do cut those down in the end because the $4 reward is just so good that we want to keep that around. Now let's try another variant that we can do. We can adjust the discount rate. So let's keep P the same. Copy this code. And we're gonna say what happens if we gradually increase the discount. We should say decrease the discount because we're going from a high certainty to a low certainty range, right? I'm going to do 0.01 because I want to see this a little bit better. I'll call this discount values. And I'm going to discount equals D. So we'll just D and let's try to do this. So as discount decreases, we'll see what the optimal action is. Oh, discount rate has to be, that's right. So let's go back to here. And it can't be 0 either, I think. Yeah. So let's start it at 0.01. And we can do a fix here to try to fix the error. And we'll accept, try to run this. Okay, so this discount factor, you can think of this as a level of uncertainty. So we're highly uncertain at the 0 mark here on the x-axis. And on the on the other hand, on the far right, we're highly certain about the future. So as we get more and more certain, the decisions start going from being cut all the trees down right away to make as much money as we can to wait and see, right? So it's a very similar behavior to what we saw for the probability of wildfire method. Let's try to vary some other things. So we could try and vary the rewards matrix. So we'll try to vary R1, actually. I think that would be really cool. We're going to vary the, we actually really vary the discount rate. So let's say, what happens if we gradually increase the award for cutting the tree? Okay. So remember that reward for cutting the trees is currently 2. And it's in this R2. So let's actually go from 1 all the way to 10. Okay, that should be really interesting actually to see. I'm so curious what this will do. So yeah, we can edit our code a little bit here. R2 values here. Just trying to fix all of the issues that we might have here. And we'll say optimal policy as R2 increases. So we'll say this is R2 in dollars. Okay, wow. Interesting. always saying that it's better to wait. Even when we have a really high reward. Kind of a surprising result. Yeah, kind of a surprising result, honestly. I was not expecting that one. But yeah, you can see these are really good things to try on your own. Test the sensitivity of your conditions to different scenarios. How will the policy change? Right? Okay, so that pretty much ends our reinforcement learning, and we're actually done a little bit early. So I think I'm going to try to cover one other topic, which is the last of these lessons in this classification workshop here. So, the first case, clustering this morning, we learned about how to cluster, how to classify eruptions as long or short. And then here we learned about how to say whether we should cut the tree or keep that, right? This last one here is going to be much more related in lesson 2 to decision trees and rainforest. Okay, and we're going to talk about a data set called kyphosis data set. Now I'm going to show you kyphosis, and I'll warn you, this is about medical. This is related to healthcare and medicine. So if you don't want to talk about that, that's okay. You can turn off the screen or pause it while we talk about this. I'm just going to show a quick example of what this is, so you can understand. It's not very bad, honestly, in my opinion. Maybe it is for you, and if it is, that's okay. But here is the diagram. Basically, some people might have some malformation. So, yeah, I won't get too into the medical stuff. I'm not much of a, I don't know anything about medicine, but we can classify this as they either have a malformation or not. So here's our data set. Let me take a look. I actually have it on Kaggle. I'm not sure if any of you have worked with this data set on Kaggle, or if you've worked with Kaggle before. I'm going to paste the data set into the chat so that you can see it. And let's share our screen here. So basically, we have two possibilities here. And this is some data that was recorded of patients who either have or do have kyphosis. And so in 80% of the patients, they did not, and 20% they did. So first, they have their age as one statistic here. That's going to be the age of kyphosis. And then this is the number of vertebrae that are affected. So you can see that usually more of these indicates that there could be kyphosis. Actually, let me look at the note here. I think there should be some note. Yeah, not sure, but the start is the vertebra start. So the vertebra start is, 1 is a really high vertebra number. It's like very almost to your head. And then 18 would be very low. Okay, so that's the idea here with this. And we're going to use these 3 variables to classify the kyphosis. And we're going to use random forest algorithm to do that. So let me get some slide up for that so I can show you. Okay, here it is. I just have a few basic slides on this to show you. So first, let me tell you about what is a decision tree. So decision tree is a supervised learning algorithm. In other words, a predefined decision scheme based on a tree model. So we're going to talk about our kyphosis model, where some of these variables, like I said, start is the vertebra where the surgery took place, age might be the age of the patient. And so here's an example of a decision tree. And you can see at each breakpoint, there's a different decision. And so at the first breakpoint, you're saying, is the start value greater than 8.5? Yes or no? So does the malformation start below this level? If it does, then it's probably not kyphosis. You can see every time that you say yes to this condition, it triggers something much more green. Then if it does happen above 8.5, it's almost always, in fact, there's a high probability, 0.58, that it will be kyphosis. Okay? So then it goes on to the next level. Does it start above 14? Right? If it definitely starts above 14, but below 8.5, it's not. But it might be if it starts below 14 too. And then it comes down to the age. So now the tree is going to decide based on the age of the patient whether this is normal. So if the age of the patient is still quite young, less than 4.6, they'll just say no. But then the age of the patient could be a little bit older, so more like 9.2 or higher. And in that case, if the patient's already quite old and still have this malformation, then it's most likely to be kyphosis. So you'll get a high variable, almost as high as if the malformation was above 8.5, that original case. And so here is just a diagram of what it looks like. You can see there's a 3D manifold here, where each level is corresponding to the probability that something might be present there. And then on the plane, on this horizontal plane, we have start and age as the two variables. And so you can see how the algorithm is built. It's pretty non-linear. You can notice that random forest is not really a linear model. And so then here's the classifications here. So you can see that the real values are the green and the red. So that's the real data from the database. And then the model itself could be showing this fake predictions. So it's attempting to classify based on this, and we can see it does pretty well. It does miss a few, so there's a few greens that are in the gray, and a few gray, reds that are in the white, but overall, pretty good. Okay, so random forest, the reason we call it random forest is because it's associated, it's taking all of these decision trees, making a big ensemble of them. So it's basically making a family of them, and each one is going to come up with its own prediction, and then they'll be averaged together. So that's the end result, really. And so, yeah, this is not a random forest. This might be kind of a random forest for us, but a random forest is just ensemble of decision trees. So you're going to take many of these, and they might be having different parameters. They won't all be the same like this, but they'll be kind of an ensemble. So let's try to do this in our lesson. I'm going to remove the codes from our blank page because we don't want those to persist. Okay, let me just delete all of these so that we have a blank slate here. Give me a minute to do that. Okay, so let's go to our VS Code module. Oh, I forgot I have to actually push that to GitHub. So let me do that right now so that you all have access. Okay, that's all pushed now, so you can see that we've updated our stuff here. And when you go into VS Code, see lesson 2 and lesson 2 blank. Oh, I guess I put lesson 2 as blank. I put this as the answer key, so that's all right. They're both interchangeable. So just open up your lesson 2. It should be blank. And so first we're going to import a bunch of modules. So we'll import a module for visualization, import some for array handling, data frame handling, and then I'm going to import several modules from the sklearn package. So the first one is called model selection. This is what we're going to get specifically. It's called train test split. It's going to split our data so that some of it is reserved for training and calibrating these decision trees, and then another portion of the data we'll use to test those out. So then the next step is to do sklearn ensemble. And here we're going to import the random forest classifier model of sklearn. So that means we don't have to build this decision tree ensemble thing ourselves. We're going to get it from sklearn. And the next thing we'll do is get the decision tree classifier. So I want to show you how to compare the decision tree classifier to the random forest. Show you why it makes sense to have that. And so then we'll import a bunch of metrics. So we'll import confusion matrix, accuracy score, this, and I also want to import something called classification report. If you run that, import them. Awesome. Okay, so we're going to import this kyphosis data. It should already be available in this subfolder here, so you don't need to download anything if you already have the GitHub repo downloaded. But basically, we do read CSV, and we get the kyphosis CSV. And we'll drop the number dimension, the axis 1, because we don't want to use number. I don't actually remember what that's referring to, so it doesn't matter. We don't need it. So then I'll just you know, the F so we can see what we're looking at. Okay, so this is just like our Kaggle page. So you can see we have a table of the kyphosis result, the age, and the start. And I actually think, you know, it's 158. This person is not 158. I think this is the months old. So I think this is probably most common in kids. They probably have some way to fix that or give a therapy to fix that for adults, because I don't see any that are greater than, let's say, 12 years old in the States. In fact, let's see, what's the maximum age here? Let's do this then. Okay, 206. So they only have it up to, oh, that's actually kind of old, looking at the 18. So maybe they're just tracking it in kids, and they don't have any adults in this data set. I'm honestly not sure, but we'll just keep that as our data. Let's try to plot that actually. Okay, so there's our age. We could actually plot this where the kyphosis is absent. Here's where kyphosis is absent, and then we'll do one for present too. So here they are. Could probably argue that age. Okay, we got to put some label on this too. It's almost impossible to read. You'd probably argue that older age is associated with more diagnosis of this condition, because you see there's a ton of younger patients here, less than 50 months, less than 5 years old, and they're not getting many diagnoses at all, only 2. Whereas as you get into this range here, the diagnoses increase, and then they seem to fall off after 150 months, or maybe like 12 years, 13 years old. So then let's actually do this same thing that really wants to do, to replicate the histogram but for the start variable. Let's see if that works. I'm not sure if that'll work. Seems like it worked. Okay, there it is. So we can look at the start variable here, and you can see that as we look at these lower start vertebra, so the lower numbers indicate higher up in the body. So this means that higher up in the body, if there's some sort of malformation, that is much more associated with the kyphosis, right? So that's another dimension, but you can see it's not evenly distributed. And a lot of these points will be collinear. So there could be, what that means is that the age and the start could be related. So that's why these decision tree models are really good, because they're not linear models. So let's start with a simple decision tree. I'm going to define this called simple tree. I'm going to take 2 things, age and start. Okay. So first I'm going to say a first node. This is going to be the first branch. And what we're doing here is we're going to try to recreate this picture, okay, the one that we have from this is the one we have from our slides. So first node is if its start is greater than or equal to 8.5. Second node, so we'll say return. So if this is greater than 8.5, let's say less than 8.5, but less than 8.5. Then we'll return this 358. So we can return a random percentage here. So we would do 1 sample from 0.58. Okay. So that means that we fell into this trap here, where we went to programming. Let's do a second node. So if we start at greater than or equal to 14, this means that we did not fall into this node, we went down here. So if we start at greater than or equal to 14, we'll drop into this bucket here. So that means we just return 0. So then let's do a third node. Let's say this will be, get to here, this breaking point here. So the age is less than 4.6. In that case, we also return a 0. Now we're down to our very last node, which is age greater than or equal to 9.2. So this is the fourth node. If age is greater than or equal to 9.2, then return, remember here we're returning a probability, so we'll return 14%. And then finally on our fifth node, we're just going to return, this is not our fifth node, but this is our last step, I guess we could call it. So we'll just return that last one, which is going to be related to 0.5 step. So we do 1 equals 0.5 step. And so we'll run this code. That'll cause us to define this simple tree function. You might want to know, how can we define the accuracy of this model? So let's just try running it first. I mean, we should just try to run a model, right? So let's say we start with an age of 5 months and the start vertebra is 10. Let's see what we get. We got 1. Sometimes we get 0. It is a random binomial, right? So it's possible to get 0, but most of the time we're getting 1. So if we look at our decision tree, start vertebra is 10, so we go into this branch here, the left branch. Then we get an age of 5, so age goes down to here, and so this is this bucket here, 14. All right, so we're looking at this right here. So let's try now and evaluate the accuracy of this model. So we're going to say, we're going to make a list of all of our predictions, okay? Because we know the real values. The real values are in the Kaggle data set. So we're going to say for data in our values. So we have these different tables of values. You can see from above. There's our table. And we'll say that, you know, the prediction is the simple tree. And we do data 0, data 1, give our age and our vertebra there, and then we'll append that prediction. Or actually, I don't want to do that yet. I want to do the following. I know that the data 0 is the, oh, this should be 1 and 2. So I know that the first column, which is data 0, is actually absent or present. So I'm going to say that the actual results, to use numbers at least, we're going to say the actual results are whether it's equal or present or not. So when it's present, actual will be 1. We're going to know that present means 1, absent means 0, right? So then our decision tree will say absent if it's for 0. So let's try this. So we'll do if prediction is equal to actual. So that means they're comparable. So they made the right call, essentially. We'll append a 1. And otherwise, we'll append a 0. So this is going to let us see what fraction of the time the prediction and the actual result match each other. So then I'm just going to print that because this is predicted down here. And take a look. So most of the time, you can see, most of the time we get a 1. Right? So our model's pretty decent. And if we were to take the mean of this, take the mean, that's going to tell us the fraction here. We get 0.79. Now that's pretty good. That means that our model was accurate 79% of the time. Okay? So not bad. But let's test our score by repeating the test, right? So if we just repeat this whole test, we should get a slightly different number. Yeah, so we get 0.77. So you might have to run this a few times to really get an idea of the accuracy of the model. We actually have a code to do that, so if we just delete this, code is starting with a function, so the function could be get accuracy. And we'll just make a list of predictions just like we did before. Return the mean each time. And then we could run this so many times. So we could do accuracy scores, right? And we could run this, let's say 100 times and print out the results. So here they are. I want maybe 10 bins. It's too much. So you can see there's kind of a normal distribution here of accuracies. So this gives you a sense of how good our model is here. And now we're going to move to a random forest, right? Because obviously this decision tree is pretty good, but I think maybe we could do better if we used a machine learning approach. So the way we'll do that is first we'll do X. So X is going to be our features, like one of the forest. And you do a drop on the data set, the typhosis column. And then Y will be whether we have a 0 or 1 for our absent or present, right? So if we print out X, this is what it looks like. If we print out Y, that's what it looks like. Okay. And honestly, I think we should probably do x.values. Not sure if that's going to make a difference, but x.values is probably what we'll eventually input in, right? So the first step is going to be to break into training and test set. And the way we do that is with this train test split method. So you can see that We've put in X, Y, test size, and the random state. So X would be the features, Y would be the absent or present, and then we would have the test size and the random state. And so we're just saying, hey, randomly pick 20% of the data to be in the test range and 80% to be in the screening steps. So there's our result. And if you were to just look at some of these, it can't really tell exactly, but that's obviously much shorter, right? The exact test is much shorter than training. Can't tell if they're randomly sorted, but we'll trust the computer for them. And then we'll do a random forest model. So first we'll define a random forest classifier. And this n estimators parameter is 100. So that's the number of trees that you have. And then the random state, keep saying the random state, the reason we're setting a specific random state is so that it's a reproducible result, right? So that's the reason why we have it like this. And so we can fit the data and generate some predictions. So when we look at our predictions, let's see 0 or 1, meaning absent or present. Let's try to now take a score of these using that score feature that I mentioned earlier. This is essentially the same thing as what we did earlier, but just automated. And we get a pretty poor score, honestly. Not what I was expecting. Wonder if it's because of the number of estimators that I chose. Okay, so it's still pretty bad here. I wonder what happens if we increase our number of estimators. Let's try that. So if we increase our number of estimators, that's what's called hyperparameter tuning. So we have max estimators. And let's say we can choose up to 500 estimators. Okay. So here what I'm doing is creating a loop that is going to try many different numbers of estimators. And we're going to get the sample scores and put them in as follows. And for a number of estimators, I'm going to say I plus 1 because I'm starting at 0, and we can't have a random forest classifier with just 0 decision trees. So yeah, let's actually try and build this now. So we have our fit done here, where we fit to the training data, and then we calculate the score. And then I'm going to just have it print out I and the mean of the sample scores. Okay, oh, this should be like that, so that we have an integer there. Okay, this is more what I expected. I'm not sure exactly what was happening before. But you can see as we get more and more estimators, we get a better result. And then something funny happens. Once we get enough estimators, our improvements in the score tend to get lower and lower over time. And so let's stop this for a minute, because I want to actually record these values. I'm going to record them in 2 variables. The first one's going to be number of estimators. The second one's going to be average accuracy. Okay? So let's actually record some of these into the lists here. And I'm going to take this down a notch. I don't think we need to do 500 of these. So let's just take it down a notch to 100. So you can see we're getting closer and closer to that 0.8. Oh, just broke 0.8 at 70. Now we're back down below 0.8, but not by much. I'm actually going to get ready because we're about to finish, actually just finished the code. So I'm going to plot let's just do a plot of the number of estimators as a function of average accuracy. So you can see what we got here. This is what we call a training curve. And so it basically represents how accurate the model is as we increase the hyperparameter. And you'll notice that as soon as we get to a certain point where we're training like 20, 40, 60 models, 60 estimators, we're not getting much benefit from having additional ones. So we see kind of a plateau here. And it indicates that probably we don't need more than 20 estimators. If you go back to our decision tree analysis, the accuracy of that model ranged just below 80. And the accuracy of this model is hitting 80 now. So we're doing a little bit better than even the best human-made decision tree. Okay, so that's a reason why you might want to use a random forest. And yeah, I wonder if there's any question about that. Yeah, so before we continue, maybe I'll just try this on the test set, because that's kind of an important thing too, to see what the test set looks like. So this data, these scores are actually for the test set, but let's try for the training set. So we'll do train scores. I'm going to do the training set each time too. I think this will be really interesting for us to look at. So let's have a look at this average training accuracy metric. So we'll just add it, I think. We've added as a line for us to check out. Now it's probably going to be quite a bit higher than the testing accuracies, but we'll see really soon. Okay, so you can see our training accuracy, it basically reached almost 100%, right? And you might think to yourself, oh, wow, that's great. Our training data set reached 100%. That means our model is almost 100% accurate. But in reality, that's why we have this testing layer, to make sure that our data set is not overfitting to the training data, and that it can still work pretty well for stuff it hasn't seen. And that's definitely true of this test data. So it's never seen it before. For that reason, it's a lower score. It's still quite impressive at 80%. That's a really good result in this field. So, okay, I hope you enjoyed learning about reinforcement learning and also taking a look at random forest since we had some extra time. And the next stream is going to be Alberto's stream. He's going to be doing Intro to GraphQL Part 1. So let's see. We'll find a check-in link for all of you to attend. This is starting in just about 15 minutes. So if you're interested in GraphQL and learning about that, definitely take the time to join. All right, everyone. Thanks again. And I hope you enjoyed, and I hope you have a great rest of the Global Hack Week. See you next time.